So as indicated, the topic today is stress relaxation study of ultra-fine-grained aluminum alloy through combined constrained groove pressing and cold rolling. There are many keywords like stress relaxation, ultra-fine-grained. I'll try to focus a bit of those before going to the actual topic of presentation. And I represent IIT Madras, which has been recently recognized as an institute of eminence. And I'm proud to represent the institute which has bagged the NIR of ranking #1 for 5 consecutive years. And also we have been recognized recently for the achievements in the for our innovative achievements. And it's a very vibrant institute with 16 different engineering departments and more than 600 faculties, around close to 9,000 students. And unfortunately, all of them are at home. We have less than 200 students inside now due to the pandemic. Coming to the present topic, I will first give a brief introduction on the severe plastic deformation before introducing the recently proposed route by our group, namely CGP plus cold rolling. And we will also discuss briefly on a particular method called stress relaxation to quantify the degree of grain refinement. With that, I will conclude the talk. So this topic focuses on aluminum alloys. Traditional pure metals of aluminiums exhibit poor strength that limits its applications. Although it has many suitable physical and functional properties, the minimal strength limits the applications of aluminum alloys to a wide range of structural and functional applications. Of course, there are standard solutions of alloying the pure metal and by utilizing the physical metallurgy based strengthening mechanisms, namely solutionizing, precipitate hardening, grain size refinement, and strain hardening. So we will be focusing on the strengthening mechanism using grain size. So it is well known that once if you reduce the grain size, the strength of the material increases. So the next 1 or 2 slides is for the sake of students who are listening to this from physical metallurgy point of view. Oh yeah, this is to tell you that the size or grain size matters a lot. As I said, when you reduce the grain size, obviously the strength increases. But if you keep on reducing the grain size in metals below a certain level, the material tend to exhibit some extraordinary properties that are suitable for many applications, not limited to the strength. The schematic representation of an elephant and ant is to show that when the size reduces to an ant level, the ability of the ant to take load much higher than its own weight is an indicator that grain size matters. So this slide is for the sake of students. We all do not question that a polycrystalline material is stronger than a single crystal. Now, if you hypothetically take a single crystal, it is characterized by the slip orientation, assuming that we are talking about cubic metals where the plastic deformation mechanism is predominantly slip oriented. Now, the right side shows a schematic stress strain curve. Now, if we try to assemble hypothetically a few grains of similar orientation and form certain boundaries, typically this is not possible in a polycrystal material because adjacent grains will have different orientation. Otherwise, it will not even form grain boundary. But just assume that if we have created a structure like this, then you will see there is no difference in the stress strain behavior of such a given polycrystal with respect to a single crystal. The important contributing factor in a polycrystal material is a geometrically necessary dislocations that generates additional dislocations and contributes to increased strength. So by keep on reducing the grain size, we can increase the strength of the material. So strength is inversely related to the grain size. So that led to the famous empirical equation due to Hall and Petch, where it is proved that the strength increases inversely to the square root of the grain size. But in addition to the strength, the schematic representation also shows the slope has increased significantly. That is, in other words, the strain hardening. So that can be easily shown if you equate the total plastic work. Let's assume, please ignore the detailed math. All I'm doing is equating the total plastic work in individual grains and equating to the plastic work done by a macroscopic polycrystalline material. And this is connected by a Taylor factor with all assumptions involved, of course. In such case, the strength is scaled by the Taylor factor m, whereas the first differential d sigma by d epsilon, which indicates or which essentially kind of quantifies strain hardening, is increased quadratic when compared to the single crystalline material. So that's the reason why you see a strong slope in the case of polycrystalline material. Now that said, if you keep on decreasing the grain size to very small levels, you can increase the strength infinitely, but not so. There is a limit to which Hall-Petch equation holds, after below which there are other mechanisms taking into picture. But I really want to emphasize that the ultra-fine grained materials should not be necessarily viewed as a strong material. If the requirement is only to achieve a structurally strong material, I would say honestly that the ultra-fine grained material is actually an expensive solution. You should go for heat treatment or alloys, which is with the chemistry available, which is much more easier to achieve the strength. But what is interesting is the other properties, whether it is physical, chemical, optical, that enables a wider range of applications in scenarios like sports, medical, space. For example, in that I have indicated 2 review papers, they have mentioned that the hydrogen absorption capability of an ultra-fine grained material is far superior than the base metal. So that can be used for battery storage or hydrogen storage vessels. And so such kind of applications. Even recently, we showed one such application where we were able to improve the antibacterial nature of copper by subjecting it to ultra-fine grained refinement. So these kind of multiple applications is what more attractive, not just the strength-weight ratio for structural applications. Now, one issue in creating such ultra-fine grain using the conventional heat treatment is the competing mechanisms of grain growth. So there is a lower limit of grain size you can achieve by traditional heat treatment. So another alternate method is to use a severe plastic deformation. Severe plastic deformation refers to a range of manufacturing processes that capitalizes the use of plastic deformation to break the macroscopic grain to fine grain size. So what I show here is a list of many processes that has been developed over the past 2-3 decades. So one challenge in all these processes is to scale it up. How to produce bulk nanostructure, which is commonly used to refer the ultra-fine grain. But I use the term ultra-fine because not all the severe plastic deformation methods produce grain sizes of nano level. So it is better to call ultra-fine grain. So one of the challenges to produce bulk nanostructured materials through these processes. There are few processes which can be scaled up. So 2 such processes for sheet metals are cryololling and constrained groove pressing. I'll just briefly tell what is that. I think many of you might have known what is cryo-rolling. It's just a conventional cold rolling process performed at cryo condition. So it's actually simple and scalable. All you need is to reduce the temperature of the plate. So the challenge is to maintain the low temperature. So right now we are using liquid nitrogen bath to maintain the temperature of the workpiece. But you know that rolling is usually done in multiple passes. So each pass we have to soak it in liquid nitrogen, and therefore the lead time increases significantly. And that's the negative part of cryo rolling. And coming back to constrained groove pressing, there is a claim that it is mainly suitable for ductile materials only. So recently, we have shown that by modifying the geometry of the dies, those can be overcome. So I'll first focus on this CGP process. We have used the 6000 series of aluminum, which is a well-known material. What you see here is a schematic of a constrained groove pressing process. So it has two sets of dies. One is as you can see, a grooved die. Other is a flat die. So the process is very simple. We start with a flat sheet and subject the flat sheet between the corrugated dies. It will form corrugations, and then immediately we flatten them. So this formation of corrugations followed by flattening induces an intense shear strain in certain alternate regions in the metal. Now, at the end of these two stages, we repeat the same by introducing shear and reverse shear in the, again, alternate regions which were not deformed. We achieve this by rotating the sheet by 180 degrees. So that's because your dies are not symmetrical. So by rotating 180 degrees, you can catch hold of those areas which were not deformed earlier. So these four stages constitute one pass. At the end of one pass, each region in the material would have undergone one cycle of shear and reverse shear. So as you increase the number of passes, we can increase the degree of grain refinement. So most of the severe plastic deformation, including CGP, relies on inducing large shear stresses or shear strain to achieve plastic deformation. Otherwise, under pure tension, the material will fail by necking. We also try to impose large hydrostatic stress to postpone the failure by necking and fracture. So this is an actual setup what we use for constrained groove pressing. So one of the biggest issue you can see here is that at the end of flattening also, we were unable to get a perfectly flat workpiece. So this is a bigger issue. Although it is well known in the community, it is not addressed. People kind of lived or accepted with these defects. So in fact we pointed out in one of our publications that the way in which we use to characterize the CGP and the strength characteristics by obtaining the specimens after a CGP process itself is wrong, because when you take a tensile specimen and do a deformation, what you see here is an actual DIC vis-a-vis our finite element calculations. It's not a uniform gauge length. So these are all some practical difficulties. So what we recently proposed, and it is published in MSCA, is a hybrid process where we combine the CGP process with a cold rolling. So at the end of CGP, we perform a cold rolling. So there are two advantages. One is we don't need to do many number of passes. It isn't sufficient to have one pass of CGP followed by a cold rolling to achieve a grain refinement in the order of cryo rolling. So since the cryo rolling takes a lot of time due to liquid nitrogen dipping, so this process is an alternate for cryo rolling, and it is also better than CGP because we flatten the work pieces by using cold rolling. Now, if you go through literature, there are many papers which are coming in the topic of severe plastic deformation, wherein multiple processes are combined and hybrid severe plastic deformation process are proposed. Most of the papers, at least to my knowledge, focus on either one of those functional properties. They focus on strength addition or a particular property enhancement. Now, I wanted to emphasize here that our focus is not the functional aspect. For increasing the strength, as I said, there are many methods. Our aim is to overcome the limitations of these processes, because that's what lead to scaling up and implementation in industry. So if I really want to increase the strength of a CGP process, you can go for cryo CGP or in fact multiple CGP. There are many methods, but that does not alleviate the obvious difficulties of implementing a CGP sheet in industry. Same can be argued for cryo-rolling. So I request the audience who are interested to work on severe plastic deformation. The fundamental work on SPD has lost its steam, but the challenge is now how do we scale up and how do we implement in an industrial scale. So for that, we need to work on overcoming the limitations, either by coming up with new processes or while hybridizing the existing process, we have to ensure at least we eliminate some of those practical difficulties. And these results are quite trivial, but I still wanted to quantify it. Obviously, when compared to a solutionized aluminum, your constrained groove pressing, which is a severe plastic deformed sample, exhibit a higher hardness and therefore higher strength. But what is important to notice is that the hardness distribution has a much broader range. So that is due to the both geometric and material inhomogeneity induced during the process. So as evident from microstructure characterization on the inhomogeneity due to the CGP. Now, when we subjected the CGP process to cold rolling, we were the cold rolled structures, especially the lamellar or pancake structures, were uniformly distributed. I'm not showing some of the other results for sake of time. We were able to show that the kernel average misorientation kind of improved when we combined the cold rolling with CGP. So in addition to obtaining a flat surface, we were also able to tweak the microstructure of the sample for homogeneous microstructure. And what is interesting is we were simultaneously able to increase both strength and ductility. Thereby, we were able to increase the toughness of the sample. So this process is quite workable. I mean, it improves both functionally as well as practically. Now, the next important question for any severe plastic deformation is to quantify the grain refinement. How much has the grain is refined? And naturally, going to optical or SCM is challenging. If you really want to work on it, because all these are substructural level, we are relying on geometrically necessary dislocations as well as your high angle grain boundaries to induce this refinement. We need to go to PM level. And simultaneously, we have to question, do we really need to that level of sophisticated microscopy only to show that we have achieved this level of grain refinement? So alternately, many people rely on macroscopic rate-dependent techniques, such as strain rate test or stress relaxation test to quantify the degree of grain refinement. So we have also used one such well-established test called stress relaxation, with which we can estimate the activation volume. So activation volume, in crude terms, we can say it's a small amount of volume of the dislocations that is essential or necessary for a deformation mechanism to be active. So by quantifying the activation volume, we know what are the deformation mechanisms that are active, and thereby we can quantify the degree of grain refinement. For example, at really ultra-fine and nanostructure levels, grain boundary sliding tends to happen that will affect the activation volume. So these are the methods. So a schematic of stress relaxation test is we have to load it uniaxially and hold the specimen for some time, and you can measure the stress drop, and then you can of course go back to continue the test till failure. So this test, the stress drop during the test can be used to estimate many metallurgical parameters, including the rate-dependent viscous parameters. So a brief introduction on the stress relaxation test. So during the stress relaxation, what we essentially do is we are actually holding the material without unloading. So the total strain remains constant. So because of this, we can the plastic strain rate is nothing but sigma dot by E. Now, once we know the plastic strain rate, then we can equate it to the classical Orowen's equation and relate to the microstructure mechanisms. The Orowen's equation for plastic strain rate is proportional to the mobile dislocation density and average dislocation velocity. Traditionally, people used expressions for velocity, assuming the dislocation density as constant, and express the an equation for stress relaxation. There are two popular equations. One is an empirical equation for dislocation velocity by Johnson and Gilman, and other one is a Arrhenius type, which is more of a thermodynamic framework. So if you substitute the Johnson-Gilman method, what you get is a power law model for stress relaxation. It has many limitations, so we are not considering that. The other option is to use the Arrhenius type of equation, and if we use that, we can actually get a simple model called a logarithmic model for stress relaxation. This is what we are using for the quantifying the stress relaxation. In this logarithmic model, the coefficient alpha is actually related to the apparent activation volume, which is what we are really interested in. So during stress relaxation, once we have the data of stress versus time, we can fit using this logarithmic model and obtain the activation volume. So from the activation volume, what is shown in the right side of the slide, you can see that the grain refinement decreases the activation volume. So this is an indication that smaller volume of dislocations are participating due to relatively small grain size. But there is an issue in this test, because in this stress relaxation test, what you see schematically here, during the relaxation, the mobile dislocation density changes continuously. So the original logarithmic model cannot be used directly, or rather it gives only an approximate information about the activation volume. So there are many experimental evidences which show that the mobile dislocation density is varying. One such experimental evidence is called repeated relaxation, where ideally if you have the stress relaxation attributed only to dislocation velocity, irrespective of the number of times you relax and reload it to the original stress, it should trace back the similar stress versus time profile. But you can see that the stress drop keep on decreasing as the number of steps increase. So this change in stress drop between the subsequent steps is attributed to decrease in mobile dislocation density. So obviously, if you go back to our one equation, you cannot treat this ρm as constant. And other recent evidences clearly show sophisticated TM pictures that at the end of relaxation, your mobile dislocation density is not constant. So I'm not going to the mathematical details. There are techniques where we can use the repeated stress relaxation stress result and thereby estimate the correct activation volume. So what we obtain from single relaxation is apparent in nature, whereas using repeated relaxation stress results, you will be able to obtain a much refined calculation of activation volume. So these are some results, and you can see the actual activation volume for three conditions: solution treated, CGP, and CGP plus CR. What is interesting is if you compare to the apparent activation volume, all of them exhibit a lower value. For example, solution treated, the apparent activation volume was the order of 240 something, and whereas here it is close to 150 to 160. It is important because the range of activation volume dictates the operating deformation mechanism. So we cannot afford to make a huge error in the estimation of activation volume. But there are challenges even in this. Our group, in fact, my students, continuing students are contributing a lot in this topic, that during stress relaxation tests, there are other complications. We already saw the variation of mobile dislocation density. In addition to that, the internal stress varies. So my student Anand Verma has proposed a sophisticated model to overcome this. And similarly, at the end of relaxation, if you reload it, you can see a small yield point-like phenomenon, which is again due to mobile dislocation density. But this is dependent on the relaxation time. How do we account for that? And similarly, when we do the relaxation, especially in dual phase materials like dual phase steel or titanium, there is a significant or appreciable change in the average temperature. So that also can influence the flow stress. So how do we separate each of these contributions? We have been actively proposing constitutive models to account for these. Thereby, we can accurately estimate the activation volume. That's one effort. The other challenge is what you see here as an activation volume or quantification of the grain refinement is essentially at the scale of a tensile specimen. And at tensile specimen level, there is a huge range of microstructural inhomogeneity. It's like a typical smallest grain size to maximum grain size. So what is its effect? If we reduce the size of the tensile sample, will it affect the activation volume? So these are some of the questions that remain unanswered and needs little more work before we can conclude the results. And to conclude a bit, we have first of all demonstrated a hybrid severe plastic deformation technique that is focused more towards eliminating some of the limitations towards scaling up and practical implementation rather than simply enhancing the established strength or other functional properties. And we also showed that the activation volume through repeated relaxation technique can be a good measure to quantify the degree of grain refinement in severe plastic deformation in general and specifically on the proposed hybrid process of CGP plus CR, which we have showed. And what we have not discussed, which is due to time constraint, is correlating this activation volume with the deformation mechanisms. So with this, I will conclude my presentation